Okay, in 17.1, the first problem I will look at is number 2. And I'm supposed to sketch this. It wants us to sketch this, so we're just going to pick a few points. So 0, 0 goes to the vector 1, 0. 1, 0 goes to the vector 1, 1. 1, 1 goes to the vector 1, 1. 2, 1 goes to 1, 2. So the point 2, 1, we're going to go over 1 and up 2. And 0, 1. So the point 0, 1 goes to the vector 1, 0. And minus 1, 0 is mapped to 1, negative 1. So negative 1, 0 goes to 1, negative 1. And so on. Let's do this in Maple. Okay, so the first one, first what we have to do is we need the command with plots. And to get the vector field, we use the command field plot. And we want to do the vector 1, x. And let's just go from negative 3 to 3. And it kind of gives us a parabola shape like we got when we plug some points in and some numbers. Okay, so the command that you're going to use for a vector field is field plot. Let's return to our notes. So if you look, it kind of looks like that parabola, those vectors, if we plot some points. Okay, let's look at number 20. Here it says we're going to use Maple. F of x is r squared minus r x, and x is the vector x, y, and r is the magnitude of x. Use the Maple to see what happens. Okay, well, r is the square root of x squared plus y squared then, and so we have f of x equal to x squared plus y squared minus 2 times the square. This is 2r. Okay, to plot this in Maple, let's go back to Maple. Okay, we're going to field plot x squared plus y squared minus 2 times the square root of x squared plus y squared times x. Okay, and then the other half is times y. And then I'm going to go from, again, -3, and y is going to go from -3 to 3. Okay, and it looks like inside there, it looks like a circle without any vectors. So what we notice here that all vectors are lying on lines to the origin. If you drew lines through 0, 0, 0, the vectors would lie on those lines. They're shorter near the circle. That circle has radius 2. They're shorter near radius 2, and then they go out and get larger. And then let's look at their direction. Let's go back to our notes. So we have f of x equals 0 when r squared minus 2r equals 0, or at the point 0, 0, or the vector 0, 0. So when r is 0 or r is 2, then our vector function 0. So let's see, when r squared minus 2r is less than 0, and okay, let's see, that's going to make this a negative x, y. So when you have x negative and y positive, that's going to make the vector positive and negative. Let's try all the cases here. Okay, so case A, when the point is negative, when x is negative and y is positive, you're in quadrant 2. The vector is going to be positive, negative, so you're going to go positive, negative. It's going to point in. When x is positive and y is negative, the vector is going to go negative, positive. It's going to point up. When you're in quadrant 3, where x and y is both negative, your vector is positive, positive. And when you're positive, positive, you're in quadrant 1, then your vector is negative, negative. It's going to point down. So all these, the vector points towards the origin. Okay, when r squared minus 2r is greater than 0, that means you have a positive vector. If you start out in quadrant 1, then vector's going to be positive, positive. If the point is negative, positive, then your vector's negative, positive. And if you're negative, negative, then your vector's going to be negative, negative. So when you're in quadrant 1, your vector's going to be positive, positive. It's going to point away. when you're in quadrant 2, you're going to go negative, positive. Again, it's going to point away. When you're positive, negative, we're in quadrant 4, it's going to go positive, negative. You're going away. And when you're in quadrant 3, you're going negative, negative. So these are going to point away from the origin. So that's the direction. And again, the length, they get longer as you go away from the circle r equal with radius r equal 2. Okay. Number 24, the function is x cosine y over z, and we want to find the gradient vector. Well, del f is the first partial with respect to x, that's just cosine y over z. First partial with respect to y, so x is a constant. The derivative of cosine is negative sine y over z. And then you have to do another times 1 over z because z is a constant. With respect to z, again, x is a constant, negative sine y over z, but then I know that the derivative of y over z is negative 1 over z squared, so that's going to be positive over z squared with a y. Okay, let me say that again. That was correct, but I'm going to just repeat it. X, derivative of cosine is minus sine. Then the derivative of this inside is y over z squared negative. So that's the gradient field. Okay, for 28, we're going to use maple. And it says if your function is sine x plus y, we want to plot the gradient vector field together with the contour map. So the gradient vector field is cosine x plus y, cosine x plus y. And let's go to maple. For 28, we're going to say let's define G to be the field, the vector field or the gradient field. I'm going to go from -3 to 3 again. We can always adjust it. Suppress the output because we're just going to display these at the end. H is going to be the contour plot because it says plot the gradient field and the gradient vector field with the contour map of f. So the contour plot is going to be of f. And then display. Okay, so that's pretty interesting. The contour map are the lines, and they alternate directions. So if you notice, the gradient vectors are perpendicular to the level curves. So we can say that. I won't write this down, I'll just say it, that the gradient vectors are perpendicular to the level curves. And where the level curves are closer together, the gradient vectors are longer. So you noticed again that the vectors are longer when they're on the level curves than when they are over here. Here they're longer, here they're shorter, and they're orthogonal to the level curves. So that's what they wanted you to notice. Okay, I hope this helps you with your problems.